Let's review by doing a Gauss's law problem for an insulating sphere and then the electric field and the potential connection there. Here we have an insulating sphere of radius r and positive charge embedded uniformly throughout. And we want to derive expressions for the electric field and the potential as a function of little r, first when little r is less than big R, and then later when it's bigger. Initially, what we need to do here is we need to say little r is smaller than big R, where r less than big R. We're going to use Gauss's law to figure out the electric field. Q enclosed divided by epsilon naught is equal to the integral of E dA. This is a uniform sphere, so the charge that's enclosed is equal to the volume of that Gaussian sphere, 4/3 pi little r cubed, multiplied by the charge density, which is rho. The surface area of this Gaussian sphere is 4 pi little r squared. What happens here is the 4 and the pi cancel. I've got an r squared there, so I can cancel out 2 of those there. So the electric field here is going to be rho r over 3 epsilon naught. So that's for r less than big R. Now, if we want an expression for the potential is essentially the line integral of E with respect to r. What we'll do here is we're going to integrate this from 0 to little r, and then we're going to put our expression for the electric field in here, which is rho little r over 3 epsilon naught. Rho and 3 and epsilon naught, those are constants. You can pull those outside the integral, which means we're left with integrating r dr. And that comes out to 1/2 r squared. And we put our limits in of r equals 0 to r equals r. And you can see for yourself, I think, that that's going to simplify to rho r squared over 6 epsilon naught. So that's what we've got there. Now, if we go to a value of little r that's bigger than big R, so now our Gaussian sphere has this larger radius here, what's the electric field going to be? We'll do this again. Q enclosed over epsilon naught is equal to E dot dA. The charge that's enclosed is 4/3 pi big R cubed multiplied by rho, because the charge only extends to a radius of big R. This dA is the same as it was before, 4 pi little r squared. That leaves us with the electric field. Let's see what can cancel. 4 pi, but the rest of that can't be canceled. So I'm thinking here that we're going to see rho big R cubed in the numerator. In the denominator, I'm seeing 3 epsilon naught little r squared. All right, I don't want to take the time to deal with the potential as we get further out, aside from if we do a quick graph. And let's see if we can make a little bit of sense out of it. If we graph the electric field versus little r, and at some point little r has the value of big R right there. According to our top equation, this graph should be linear up to there. And then beyond that, you can see this last equation, it should fall off proportional to 1 over r squared, not equal to, proportional to 1 over r squared. Now, if voltage or potential is the line integral, what would that mean? Well, you can see from this equation in the middle here that the potential grows proportional to r squared, which is what you get when you integrate something that is proportional to r, right? Well, what would it look like on the back end here? If we integrate something that is proportional to 1 over r squared, won't it be proportional to 1 over r? So it will fall away, but at not as great a rate as the electric field does. So we took a little bit of a shortcut there at the end, but I think that's good enough for today.